All right. Our next speaker is Kevin Brinson. Kevin's with the Delaware Center for Environmental Monitoring and Analysis. He's going to talk to us about climate trends and perhaps some about how that relates to extreme weather. So with that, Kevin?
All right, thanks, Gordon. Can you hear me all right?
Yes, we can.
All right, great. All right, so thanks for inviting me to talk a little bit about weather and climate, Gordon. As the title says here, we're going to look at trends in climate and extreme weather. Hopefully, you'll get a little bit of information about some of the things you probably have some intuitive knowledge about, but maybe you'll see some of the data that kind of goes in behind it and supports it. So before I kind of get started, I just want to point out a good resource if you're looking for some information on how climate indicators relate to some agricultural criteria that are probably very important, well, to all of agriculture, but including fruit and vegetable growers. It's a new resource that came out this summer from the USDA. It's called Climate Indicators for Agriculture. I put the link here at the bottom if you want to I guess maybe the presentations will be available later. But it's nice. It has some effect, highlights some the effects of climate on weather, particularly weather as it affects agriculture, pest, disease, crop, livestock cycles, and of course even some socioeconomic factors such as productivity insurance and working conditions. And so I took some of the concepts from that this report and kind of incorporated them into this talk today, as well as bringing some local information, some local climate data that we have through our center and our climate office. So, climate indicators, that's a sort of, I'll say it's a little bit of a climate data wonky term, but basically what it's trying to say is that these are climate factors that can affect various, real world things, whether it be biological factors or in case of agricultural phenological factors, of course, socioeconomic as well. This chart you see here on the left, basically showing how different indicators have data available for them, or maybe in some cases don't, and also how they're linked to climate change, or really even just say climate in general. And so you can see things such as a lot of these natural physical indicators such as heat and temperature, humidity, soil moisture, things like that. We have a fairly good amount of data for them, but others, maybe more of the biological indicators. We have more limited amount of data available. Some places we have a lot of data, but it's maybe just not as widespread across, say, the whole United States or even the whole world as we would like. So what that means is that we have to be careful how much we read into some of these indicators, because if we don't have a sufficient amount of data to support what we're trying to understand about them, we can't say anything with too much certainty. So as I go through the talk today, I'll kind of mention where we feel that we have some confidence in things, where we maybe are a little less confident in what's going on. One thing I also want to mention before we kind of go into some of the data is climate data is a bit about trying to pull signals from the noise. And if you want to think about it, these are kind of like radio signals, where you're trying to tune your dial a little bit to get that, that sound, that music or whatever to come through. Climatologists kind of do the same thing with a lot of the climate data. We're trying to, kind of remove the weather data, if you will, which is more or less the noise, because that's a lot of, a little bit of static around the main signal. But climate is the main signal we're trying to understand. So climate's where we get our trends primarily, whereas weather kind of gives us those little spikes and dips, those extremes that we kind of see and experience on a regular basis. But so what I'll be kind of focusing on today is more the trends, or what we might call the signal. And of course, tuning the radio is always the kind of the trick here when it comes to our data. So climate trends. The first the first factor that most people think about when it comes to climate trends is temperature. This graph here shows the trends in climate temperature since basically the beginning of the 20th century. We've gone about 1/4 degree Fahrenheit per decade as an increase. from the beginning of the 20th century. So we started out around 53 at the beginning of the 20th century, and now our mean annual temperature is around 56. So we've gone up about 3 degrees over roughly the last 120, 125 years. It's not an insignificant increase. It may sound like a pretty small increase, but if you think about it, that's a pretty significant increase, from where we started. Certainly, there are projections that show a much larger increase in the future, depending on, some different greenhouse gas scenarios. But this is just a historical trend that you see here before you. If we kind of look at the seasons, it kind of breaks it down a little bit in a somewhat interesting way. The trends are stronger in some seasons than others, particularly the winter is where we've seen the largest trend. Of course, that has implications for different types of agricultural systems, including fruiting trees and how they overwinter, but also maybe in terms of how we see some trends in future precipitation and that sort of thing. But generally, the trend is across the board around 0.2 of a degree Fahrenheit per decade, with the trend being slightly stronger. Slightly stronger in the winter. So that's where we've kind of got to, I'll kind of get into a minute later how that affects some things. Looking at our maximum and minimum temperatures, and of course that can affect those minimum temperatures are really important in terms of affecting how our growing season length changes, because obviously that's when we see our minimum temperatures, our lowest temperatures throughout the day. And you can see that the trend is actually a little bit stronger with the minimum temperatures than with the maximum temperatures. Not much different, but a little bit different. And that actually is, bears out in a lot of the larger, regional and even national trends as well. So this is, again, for Delaware. And that trend, if it continues, means that our growing season would potentially become longer and longer, which I'll kind of show you in a minute. So growing season length, this is again for this graph here is for Dover, Delaware. In fact, most of what I'll show you today are for Dover, just because it's the middle of the state. And while it doesn't represent the whole state, we do have some variability. It is probably indicative of probably where more of the agricultural land in Delaware is located. So what's interesting is this: around the beginning of the 20th century, our growing season was roughly about 195 days. Now we're up to over 220 days. Obviously, it varies from year to year, but again, this is the trend. So the trend is about 2 days per decade longer for our growing season. So now we're getting about 3 weeks more growing season, longer growing season at today than we were around the turn of the 20th century. So that's a pretty significant change if you think about it. And of course, as you might imagine, if you have a longer growing season, you might see fewer days of freezing temperatures. And that bears out in this graph you see here. Around 2 fewer days per decade of freezing temperatures. Starting up around 100 or so in the early 20th century. And now, we see fewer than 80 days or around 80 to 90 days per year. So, decent decrease in number of days below freezing. Of course, if you have days below freezing, that can affect your chilling hours. And of course, I know chilling hours can vary depending on the type of fruit, in terms of what temperature you use for the calculation of chilling hours. This example here, and I apologize, it may be a little hard to see here. This is again from that report that I mentioned earlier. This shows chilling hours for apples in Poughkeepsie, New York. This was a data set that was maintained by Cornell University. And what's important to show here is that for the different phenological steps here, green tip, tight cluster, and full bloom, you can see that the stages were 4 to 7 days earlier from 1980 to 2015. That's not an extremely long, from a climate perspective, not an extremely long period of record, but it's still, a decent sized record, 35 years. And we saw a change of almost, a week change in those the timing of those stages, and those stages are closely tied to changes in the temperature patterns that we've talked about in the region as well. So that's it's all kind of connected to our changes in our temperatures over the last 30 years to a century. Um, and of course, that would have impacts on other fruits as well. So that's something else to keep in mind as far as the chilling hours are concerned. Late freezes and sort of late freezes in spring and early freezes in the in the fall, we have seen some changes in there. And what's interesting is that our growing season has changed significantly, primarily not because the fall is necessarily getting um, starting later. It's actually because our spring seems to be starting early. We're kind of getting into spring a little quicker than we used to, and that kind of shows up here a little bit where our last freeze is. And second, I'll show you where the first freeze in the fall is. So this red line here is sort of our decadal average. It's a moving average of over a 10-year period. And what you notice is that it's a downward trend in the last freeze date. So back around the early 20th century, the last freeze happened sometime in mid-April, basically. Now our last freeze, on average, again, this is not a every year is the same, but is happening around the beginning of April, even the end of March in some cases, on a more regular basis. And again, this data set's for Dover. These departures, what's I think important to show you about this graph, this is showing you basically how far that last freeze date differs from sort of the mean or the median freeze date, which that's not November 4th. I'm sorry, I apologize for that. It's not November 4th there. But what's important to show you here is that the variability is pretty much pretty minimal. So it's not that the freeze date is necessarily varying more wildly. We haven't seen an increase in the variability of the last freeze date, but we've seen a change in the trend. So the freeze date is happening, the last freeze date is happening earlier, which is indicative of the growing season trend I mentioned earlier. The first freeze date is perhaps a little less of a significant trend here. You can see that the last freeze was happening in sort of primarily late October. Now it's more towards the end of October, early November. So it's changed maybe about a week or so over the period of record. So the first freeze of the fall, it's not where we've seen the most change in the timing of freezes. Our timing of changes has mainly been in the spring. I guess one thing I just want to point out here is that we do see extremes from time to time. In 1924, they had there was the first freeze in Dover took place on September 8th. I just can't imagine what that would probably be like and how that would affect so many of our crops right there. But 1985 is on the other end of the extremes of the spectrum. That was December the 3rd. So that's just, I mean, another example that we do have some wild swings from time to time. But in general, the trend is showing a slightly later first freeze. This is just once again showing the freeze date departures. And once again, it's the same thing. Not a whole lot of changes going on in terms of the variability. We are just seeing a slightly longer trend or later trend in the first freeze date for Dover. Another impact or climate indicator is insect generations. The number of generations of an insect that you can see is obviously you can have a significant impact on how many times you have to maybe take preventative measures to mitigate the effects of the insects or the pests. One example here is maggot fly pests, where it would be cabbage, onion, and seed corn. Their hatching rate is highly correlated to air temperature, though of course it varies a little bit from species to species. For our region, it typically happens in April and May. The crops primarily affected were vegetables, corn, and soybean, depending on the particular type of fly or species. So I'm not an expert on those particular pests, but that's, it does seem to have some specific hosts that they go with. So this is a graph for a cabbage maggot looking at degree days, and this is again from Ithaca, New York. This is Cornell does a lot of tracking of various species of pests and disease, and have been doing it for a long time. And so that's why you see a lot of these examples in my presentation here. But what you'll see is the seasonal degree day accumulation has shown a bit of a trend in their case, kind of going along with the increase in the temperature, the mean temperature for our region. And what's significant here is that, in this particular location, Ithaca, New York, they saw, maybe 2 or 3 generations of these cabbage maggots in the early part, back in the mid 20th century. And now they're seeing more often the 4th generation come off. And of course, that has management implications for their crops. In Delaware, I haven't looked into the data on this, so I just want to say that I don't know what the impacts of degree days are for Delaware, but it's something that maybe we can look into at some point here. How might changing temperature trends? So this is kind of a summary slide of how these changing temperature trends are affecting our vegetable and fruit production. Warmer nights in general, and of course that has its implications for disease particularly. Fewer freezing temperatures, so we have a longer growing season. Again, I said before, 3 weeks or so longer since the beginning of the 20th century. The warmer winters are relative to other seasons, so there's a greater susceptibility in some ways to early and late freezes. And again, as I said before, the variability hasn't been changing dramatically, which is a good thing, which basically means that even though we're trending towards having, an earlier start to our growing season, and maybe a little bit later into our growing season, we haven't yet seen where we've been getting a lot of, sort of false springs, if you will, where we have a bad freeze happening after the, beginning of the growing season. That doesn't mean it's, we don't have those from time to time. We certainly have over the years, but we just haven't seen it in the data yet where we've had that greater occurrence of those happening, at least not in the data we have for Delaware. Another implication here, of course, with the temperature changes is there are fewer chill hours. And, because that can, depending on the particular fruit, that can be a significant factor. And then one other factor we probably lose sight of sometimes is changes in pollinator activity. There's been some studies on looking at how pollinator activity relates to the timing of different stages, particularly the flowering stages of various fruits in our region. And so far, the changes haven't been significantly different, though I think there are concerns that if climate change projections come to fruition, the timing of pollinator activity may not always be in sync with when flowering patterns or flowering stages are occurring. So that is something to kind of keep an eye on as we go forward in time. Of course, the other side of the spectrum that most people look at with climate data is precipitation. This graph here shows you the statewide mean annual precipitation. And you'll notice there's a slight upward trend, just a few inches change over the period of record of about 120 years. So about a 1/4 inch of additional rain, if you will, or precipitation per decade. Of course, precipitation in Delaware is highly variable. We have as many as, some places, have 60 inches on average in some years, and some years we have less than 30. So annual precipitation is always a highly variable climate parameter for our state, as we all kind of know. But generally, the trend is on the upward trajectory. Breaking it down into seasons, it really, you might notice there's very small trends here for most of the seasons. Winter, it's a couple of hundredths of an inch. Maybe spring a little bit more than that, around 0.8 of an inch. And then in summer is actually almost no change, by maybe 1/100th of an inch less per decade. But the only season that really shows any significant trend in precipitation is the autumn or the fall. And a lot of that has to do with some increases in essentially tropical storm activity that we've seen in say the last couple of decades in our state. They typically arrive in our state around September, October, and of course that they always bring a lot of precipitation with them when they come through our region, and so you see these larger values here in the fall that have kind of made the precipitation trend significantly higher in the fall relative to other seasons. And actually that trend in the fall actually accounts for most of the change that you saw in that annual precipitation trend as well. Another factor looking at moisture is dew point temperatures. Higher dew point temperatures, of course, can lead to increases in leaf wetness duration, which is a major factor in plant disease. The map on the left here is just showing you where the trends are in the United States, and where you can see is that our region here, the trend is around 0.08 degrees Celsius per year, and that may not sound like much, but it adds up over time. And what's really important here, to think about is our dew point temperature trend significantly higher than our temperature trend? And actually it is. It's around, if you look at that and you extrapolate out since 1947, it's around a 5-degree increase in dew point temperature, whereas our temperature trend is only around 3 degrees. And so what you can think from that is that if you get your dew point temperatures higher, and if you know a little bit about how dew and fog are forming, basically it's when your air temperature and your dew point temperature are equal. So you get 100% relative humidity, and then you get condensation. So you get dew or fog formation. And that basically could become more likely to happen if your dew point temperatures are consistently higher than they have been in the past. So that trend in dew point temperature can have a significant impact on the number of hours that we'd expect to see a leaf wetness increase. And of course, that would have impacts for as I mentioned before, for disease, particularly things like downy mildew and other things like that. So how might changing moisture trends affect our fruit and vegetable production? Kind of going back to before, more frequent rainfall, which can be a good thing, right? We would love to have, rainfall happen, particularly in the middle of our growing season. Decreases our dependency on irrigation. But it can also be good for lowering evapotranspiration during dry periods. So if we have greater humidity in the air, maybe we don't need to irrigate or in between rain events. Wetter soils, that can be good and that can be bad depending on what you're concerned with as far as pests and pathogens. But the other side of that is an increase in leaf wetness duration, which again can lead to increases in disease and pests. And of course, moisture levels can also, if we have higher moisture in the air, that can also affect stored produce. So, lowers the drying rate, if you will, in some cases. So that little sword there is kind of a, silly graphic, but it's kind of showing that moisture can be a two-edged sword when it comes to, impacts on agriculture. Gordon kind of asked me to look a little bit at stormy weather to see how that's affected by our climate change or climate trends over time. One thing I kind of just want to mention up front is that the #1 natural hazard in Delaware is coastal storms. Many of you who lived here for a long time know that very well. And when I say coastal storms, I'm talking about things like nor'easters and tropical storms. Delaware averages about 32 coastal storms a year. Now, most of those don't affect us at all. In fact, most of them just kind of spin off the coast and form well off our coast and move out, and we don't see much more than a breeze that's or maybe a little bit of rain. But occasionally they do have some significant impacts, and those impacts include coastal flooding, heavy rain, high winds, and of course sometimes we get snow and blizzards with those. What you'll see in that graph on the right is that there really isn't an upward or downward trend in our coastal storm frequency since the mid 40s. It's really more cyclical, in nature in terms of when we have storms and when we don't. There's been some studies that show that the El Nino and La Nina, you may have heard that climate indicator or that sort of climate teleconnection, it has an impact on our weather in this region. In fact, in coastal storm frequency seems to be related to that. El Nino years, we tend to have a bit more, a higher number of coastal storms off the eastern United States than we do during La Nina years. And that just has to do with the effects of El Nino and La Nina on the atmospheric circulation pattern, primarily what's called the jet stream. So we have a more active jet stream over our region and to our south, actually, during El Nino. And when you have a more active jet stream, you sort of see more storm activity, and therefore you get a greater likelihood of coastal storms, particularly things like nor'easters over our area. So that's just more say that there's not really a climate trend here. It's more of a natural cycle that's taking place that's driving our coastal storm frequency. Looking at extreme precipitation, this graphic on the right is from the National Climate Assessments, looking at the changes in what's called the 5-year rain event. And if you think about it, it's just a heavy rain event that happens fairly frequently, but not it's not an extreme precipitation event, not like 10 inches in a day or something like that in Delaware. So basically what this is trying to show you is how has that changed regionally speaking over these different time periods. So from 1901 to 2016 here on the left, and from 1958 to 2016, kind of looking at the whole period of record, and perhaps you could say the latter half of the record. And what's the key takeaway here is that in the Northeast region, the 5-year precipitation event, if you will, has increased by 27% since 1901, and by about 55% since 1958. So our, if you will, our extreme precipitation events are changing. They're becoming, at least in terms of magnitude, larger over that time period. So the doesn't speak to the frequency of those events, but at least it speaks to the magnitude of those events. We took some data a few years ago and looked at how the frequency of large precipitation events are changing in Delaware over the last, over basically most of the 20th century. And this is for Dover. And I apologize, these trend lines, you can kind of see them. They're really dotted here. They didn't come through very well on this slide, so I apologize for that. But what you'll notice is that for 1 inch, 2 inch, 3 inch, and 4 inch events, there's not a large change in the frequency of these events. These frequencies are in, this is an upward trajectory, but the frequency change is around 0.1 or 0.2%. So not a lot of change happening in some of these, I'll say large precipitation events. Not that 1 inch is necessarily a large one, but one of the problems with doing extreme precipitation studies is that we just don't have a lot of extreme precipitation events to begin with. Getting how many times do we have 1 day totals greater than 4 or 5 inches? It's not that often. So looking at that type of climate phenomenon is not as easy to do when you just don't have that many cases to look at. So bottom line here is there's just not enough data or enough of a trend here to say whether or not we're seeing more frequent heavy precipitation events. Looking at hail, wind, and tornadoes, those are the 3 main severe weather types that we expect for our region. I just wanted to kind of show you the graph, not because this is meaningful, and I just want to kind of say that right up front. You might look at this and go, oh, look at an increase in wind events. This is not because, well, it's not simply because. There may be something underlying here, but it's almost impossible to discern. This is not because we've seen an increase in the number of severe weather events, severe weather systems that cause these severe weather events, whether it be heavy thunderstorms or even landfalling tropical systems that sometimes cause severe weather. What this is basically showing, or what's causing this, is really changes in our observing practices over the period of record. Basically, for the last 20 years or so, we've had a fairly consistent way of looking at, of identifying hail wind and tornadoes. It's not that, we didn't know what those were before, but if they weren't being reported, then they just never were cataloged in the National Weather Service's Severe Weather Archive. And so this is what this data set is derived from. Doppler radar has been very important to our ability to identify tornadoes. Before Doppler radar, a tornado could hit a very heavily wooded area, or maybe a open space somewhere, and it did a little bit of damage to maybe some trees. But if no one knew about it, no one saw it, then that tornado would have never happened. But now with Doppler radar, we can sort of see the signature and the radar signal. And then, if some sort of small bit of damage is even noted, it can go out and be verified by the National Weather Service. But I think the one thing to kind of take away from this graph is that damage and winds are still our primary severe weather impact for Delaware, much more so than hail and tornadoes, which are not very common in our state. So our extreme weather summary basically is that coastal storms are our primary threat. I think most of you probably know that. Our coastal storm frequency trend is more cyclical than any sort of thing related to climate change, at least at this time. The trend and the strength of coastal storms affecting Delaware is kind of unknown. We haven't really looked at how are the coastal storms affecting Delaware getting stronger and stronger over time. And of course, how you define stronger kind of affects what you might see there in terms of a trend. There has been evidence that the magnitude of heavy precipitation events may be increasing, at least regionally. But looking at Delaware, we haven't necessarily seen a higher frequency in heavy precipitation events. But I think we probably need to do a little bit more research there to kind of tease out that trend, or to definitively say there is no trend. Severe weather does happen in Delaware. And of course, damaging winds are our most common impact. And again, I just want to mention is that, looking at severe weather impacts in Delaware, it's hard to look at the data and make any sort of assertions when the observing practices have changed significantly over that period of record. And I think with that, I don't know if there's much time left, Gordon, but I'll stop there. And if anybody has a question, I'll be happy to answer it.